Hello, my name is Matteo Jovino from ABB Corporate Research and the Royal Institute of Technology in Sweden. This video shows the functionalities of our framework for learning behavior trees in collaborative robotic applications. The framework allows users to evolve behavior trees with genetic programming or to learn them through demonstration. Demonstrations can be input to make the evolution to converge faster, to help the robot learning new behaviors, and to add or modify the current target. A graphical user interface facilitates the user in this process. The user can decide to start a new application or to load existing logs. In this case, the information regarding the two learning methods is fetched. In the case of the genetic programming, the current generation as well as the current best fitness score are shown. For the learning from demonstration method, it is displayed the number of demonstrations already input and the size of the tree learned this way. The user has then several options. It can visualize the initial configuration of the item for the current task, or alternatively, the target configuration. It is possible to interact with the learned behavior tree by running it on the task, displaying it, or save it for later testing and debugging. The user can start and stop the evolution at will, as well as increasing the number of generations for the next evolutionary process. It is also possible to plot the fitness for a current task. Finally, it is also possible to visualize the clusters showing the learned frame of reference for the actions executed during the demonstration. If the user decides to input a demonstration, it can choose which action to perform. In the case of pick, a drop-down menu presents the alternative items that can be grasped. In the case of place, the user can interact with the simulator to decide where to place the grasped item. At this point, the user can move around the robot end effector at will through the use of the keyboard. The movement step can be increased to move the end effector more rapidly or decreased to achieve a better precision. In this case, the yellow box is picked and placed in the kitten box. Then the green box is picked and placed on top of the yellow box. Finally, the blue box is picked and placed on top of the green box. The demonstration is thus completed and a behavior tree built in the stack of boxes is learned. In the first experiment, the task is to build a tower of 3 cubes. The genetic programming algorithm builds a stack with 2 cubes, but then, through a demonstration, the target is changed and also the blue box is required to complete the task. The learned behavior tree can solve the task if the items are randomly placed on top of the tables. In the second experiment, the task is to build a pyramid with the available cubes. The challenge of this task is that the behavior to place the green cube in the shown configuration is not available to the genetic programming algorithm. Therefore, a demonstration is required to teach the robot the missing behavior to successfully complete the task. In the third experiment, the robot has to build again a stack of 3 cubes. In this case, however, the cubes are initially stacked in the wrong configuration. The robot then needs to unstack them first and then stack them again. Here, the genetic programming algorithm is likely to get stuck in local optima. Therefore, demonstrations are required to improve the convergence rate and speed. In this last experiment, we transfer the solution of the first experiment to the real robot. Also in this case, we will stack the cube in the kitten box in the order yellow, green and blue. The setup of this experiment, we have a dual arm ABB Yumi robot with an Azure Kinect camera that uses Aruko marker detection for the perception layer.